Hello everyone, welcome to day 15 where we will be talking about sample means and the central limit theorem. Recall where we are in the unit. We're near the end. So we started this unit by talking about basic probability, two basic rules and contingency tables. We talked about random variables. We started with discrete random variables and looked at two examples of those, the binomial and the Poisson random variables, which are very useful models with a lot of possible applications. And then we started talking about continuous random variables, which were the uniform and normal distribution. We spent 2 days working on those sorts of problems to really get it. Today we're going to start with sample means and central limit theorem, and then we're going to use that theory to talk about point estimates and confidence intervals. That will conclude the second unit, and then we will begin the third unit, which is all about hypothesis testing. The goals for the lesson are to understand the central limit theorem and its key consequences. Know what the sample proportion is and how it is distributed. The sample proportion is a random variable, and so it's going to have a distribution. The sample mean is also a random variable with a distribution. We're going to talk about something called the standard error. And that's the goal for the lesson. To start with, let's talk about the central limit theorem. We're going to let x1, x2, and xn be a sample from a population. So there's this random variable, capital X, and it has some distribution. And whatever its distribution is, it has a mean, written as mu x, and a standard deviation. It doesn't have to be normal to have a mean and a standard deviation. And then we take n copies of those. Each item sampled is going to be a copy of that random variable. And what we get is another random variable that represents the mean of that sample. Okay, this mean is itself a random variable because its value is determined by chance. Its value depends on each of these random variables. Now, what the central limit theorem says is that in this situation, x bar, the sample mean, is nearly normally distributed. So it's quite close to normally distributed, and in most cases it is effectively normally distributed. And then it also tells us about the mean and standard deviation of this normal distribution. The mean of x bar, the mean of these sample means, is equal to the mean of this original random variable. Those are the same. And the standard deviation of the sample mean is equal to the standard deviation of the original random variable, but it is smaller, much smaller. We divide by the square root of n. That sort of makes sense because the variation is averaged out, or some of the variation is mitigated by the sum. Okay, in a nutshell, this is the central limit theorem. If x is a random variable with mean x and standard deviation sigma x, and we define a variable like this, which is the sample mean, then the sample mean is normally distributed, and here are its parameters. This is mu x bar, and this is sigma x bar. Now there are two caveats that need to be satisfied. If x is not normally distributed, then n needs to be sufficiently large. As it turns out, 30 is generally large enough, so n has to be bigger than 30. If n is not bigger than 30 and x is not normally distributed, then x bar is too different from the normal distribution, and so you can't use this theorem. But if x is normally distributed to begin with, then this will be exactly normally distributed. Let's take an application of the CLT, the central limit theorem. So here's an example, sample means. All right, let me first point out this plaque here that was in an elevator in Northampton, England. It said that the capacity was 24 persons or 1,800 kilograms. So that is the weight capacity, this is the person capacity. My question is, how much do those match? Like, what sort of 24 people need to be here? Could they be adult males? Would that work? That's what I want to investigate. I don't have a sample of 28 males, but if I did, hypothetically, each one being normally distributed, what can I say about that sample mean? What is the probability that 24 adult males will exceed the weight capacity? In England, the mean weight of males is 79.8 kilograms with a standard deviation of 15.4 kilograms. We model the weight of the 24 men by a normal random variable with mean 79.8 and standard deviation 15.4. Then the mean of this theoretical sample mean would be this. So this is the mean of a random variable that models my sample mean. As it turns out, by the central limit theorem, because each of these is normally distributed, x bar is a normal random variable. The mean is 79.8, the same mean as before. The standard deviation is going to be the standard deviation from before divided by the square root of 24. So, what is the probability then of 24 men being too heavy? Now, what is too heavy? Well, if it's 24 people, then that means that the critical average weight would be that many kilograms divided by 24. If the average weight of adult males in our sample exceeds that, then they are, all of them together, going to be too heavy. I do that division problem and I get 75 kilograms. So I need to find the probability that capital X bar, my sample mean, is bigger than 75, given that that is normally distributed. So I'm just going to go to Excel. I'm going to type in norm.dist, and I'm going to put in 75 for my X, 79.8 for my mean, and then whatever 15.4 divided by square root 24 comes out to. And I'm going to do comma 1 because it's normal distribution and I don't want the y value, I want the area. Okay, but it occurs to me though that I am looking for area to the right, aren't I? So that's when x is greater than. I need to do 1 minus this probability. This right here is to the left of 75. I want to the right of 75. Okay, and I think we understand how that works. So let's go ahead now and go to Excel. I have opened up a blank worksheet, and I'm going to start putting in my data. So mu x bar is 79.8. Sigma x bar is going to equal 15 divided by square root of 24. Square root of n, my sample size, the sample size of my theoretical sample. Press enter, and now it's 3.14. Okay, and the x bar that I'm interested in is going to be 75. All right, so the probability then, probability that x bar is greater than 75 is going to equal 1 minus norm dot dist. X is 75. Mean for x bar, because it's x bar that I'm interested in, is 79.8. And the standard deviation is that one right there. Cumulative is, of course, going to be 1 because I want the area, not the y value. Press enter, and there's my probability. 93.661. 0.93661, or I just round it to 3 decimal places, and that's my probability. It's actually very likely that if you had 24 men in that elevator, you would exceed the weight capacity. At what point do you adjust what the plaque says? I don't know. Okay, but that's how we determine probabilities associated with these theoretical sample means. And this is very, very important in inferential statistics. So if I look at this example, what's going on? I've got my model of the 24 weights, each one's being modeled by a normal random variable. Here's a plot of just x. And this is the plot of the distribution of x. If you look at the orange curve, this is the distribution of x bar, my new sample random variable. Notice that it has become much more narrow. The area underneath it is still 1, but because it's more narrow, it has to be higher. And this right here, this brown, is the area, the probability that x bar is greater than 75. So here's 75. And so you could maybe be convinced that this is 94%. It was because of the central limit theorem that we knew the distribution of that. Another application of the CLT is we can do the same thing with sample proportion. This is how we do that. In a recent poll, October 10th, it was found that 78% of respondents would vote for Trump if the election were held that day. For your information, 50%, according to that poll, said that they would vote for Harris that day. Assuming that to be the true proportion of Trump voters among voters in that state, or Commonwealth, because it was Pennsylvania, what is the probability that Trump would win among a representative sample of 50 voters? Now, every voter has its own leaning. You don't know how many voters you got that are in that 47%. So what we're going to do is model each theoretical person here in our theoretical sample by random variable. That is going to be this random variable. It's going to be 1 with probability p. In this case, p is going to be 0.47. And 0 with probability 1 minus p. So that's the other side of the coin, 0.53. I'm using 1 because I want to count up the number of Trump voters, and I don't want to count the number of people who do not vote for Trump because I'm interested in seeing if Trump wins this sample. Where 1 corresponds to a vote for Trump and 0 a vote for someone else. This random variable, this is actually called the Bernoulli random variable. We can compute the mean using our knowledge of random variables. That's going to be 1 times the probability of it being 1 plus 0 times the probability of it being 0. And so that just comes out to p. We can do the same thing with the standard deviation. The standard deviation of that is going to be the square root of 1 minus p. And so what that is that's the value minus the mean times the probability of 1 plus 0 minus p times the probability of it being 0, which is 1 minus p. And don't forget, we need to square both of those. So 1 minus p is the same thing as q. Remember, q equals 1 minus p. So this is going to be q squared times p plus p squared times q. I can factor out a pq from both of those, and if I do, a q is going to be left here, and a p is going to be left here. Now, q plus p just equals 1. See, if this is true, then q plus p equals 1. So this is just going to be square root of pq. And so that's the mean of our Bernoulli random variable. Okay, and we need the standard deviation of our Bernoulli random variable, and we need that because we're going to use the central limit theorem in order to get the proportion of 50 voters. That's going to be the sum of all of these. That is going to be the mean of my random variables. And I'm going to call that p hat. The hat is commonly used, this little caret above the p, for values that are estimated, like this. This is an estimation of the true proportion, which we're assuming to be 47%. Now, this sample proportion is going to be normally distributed, and it'll have the mean of the original random variable that we're summing up, so that's p, and it'll have the standard deviation of the original standard deviation divided by square root n. Notice that this is the exact same framework that we used with the sample mean. Rather than using a normal random variable or the random variable from the sample that we're sampling, we are using ether random variable because we're interested in proportions. Okay, and now the question. What is the probability of Trump winning a group of 50 voters? So I want the probability of p hat bigger than 0.5, because that means he won that sample. And so that's going to equal, because this is normally distributed, norm dist of 0.5 with a mean of 0.47 and a standard deviation of p times q. So that's the square root of 0.47 times 0.53 divided by 50. I want to know what probability is greater than 0.5. So I'm going to do 1 minus that probability. Okay, so I'm going to go to Excel. I'm going to type in my relevant information. The first thing I want to put in is the assumed population proportion. So that's going to be P. That's going to equal 47. And then I also want to put in Q, and that's going to equal 1 minus P. All right, mu P hat is going to equal my population proportion, and sigma P hat will equal, okay, so this is going to be equal to square root P times Q divided by N. Let's see, so this is going to give me an error. Okay, divided by 0, and that's going to be 50, and there it is. Okay, what is the P hat I am interested in? That is going to be equal to 0.5. So the probability of P hat, my random variable, being greater than 0.5 is going to equal 1 minus norm dot dist. Put in that P hat that I'm interested in, the mean for P hat and the standard deviation for P hat. I type in 1 there and I press enter. And there we go, 0.335. So this thing equals 0.335, or 33.5%. So there's a 33.5% chance that in a group of 50 voters, Trump wins. That's kind of an interesting thing. The population was assumed to be 47% favored Trump, but if you take a sample, there's variability in that sample. With 33% chance, you could get Trump winning. Now, Harris's population proportion was 50%. And so the probability of Harris winning is going to be much higher than that. Okay, let's summarize now. So for the sample mean, we have this distribution of things that we are trying to sample from. And if that distribution is normal, then your sample mean will be normal. If your x here is not normal, then this thing still might be normal if n is greater than 30. For sample proportion, we modeled the success of each subject in the sample by the random variable x, and then there's this Bernoulli random variable. We observed that the mean of x was p, and the standard deviation was square root of p times q. The sample proportion, which is p hat, was equal to the sum of these Bernoulli random variables over n, which was the number in the sample. This was a mean, and so you can use the central limit theorem to say something about this mean. The mean is going to be normally distributed with the same mean as the population mean, and the standard deviation divided by the square root of n. And we can use this, because it's normally distributed, in conjunction with Excel to find probabilities about the sample mean. Another example. Assume that cans of Coke are filled so that the actual amounts are normally distributed with a mean of 12 ounces and a standard deviation of 0.11 ounces. What is the probability that a single can has less than 11.9 ounces? For that, I'm going to use norm dis 11.9 comma 12 ounces, 0.11 ounces, and that's 1. This is the probability that a single can is less than 11.9 ounces. What is the probability that a sample of 36 cans has a mean of less than that many ounces? So now you have a sample of 36 cans. What's the probability that that sample mean is less than 11.9 ounces? So we've got the probability here of x bar now, which is my sample mean, less than 11.9. That is going to equal norm.dist 11.9, the value that I'm interested in. And now what's the mean of my sample mean? It's going to be the original mean, and then the standard deviation is going to be the original standard deviation divided by the square root of 36, which is just 6. And that's going to be 1 again. Equals, okay, let's hop over to Excel and see how these compare. So the first one, the probability that x is less than 11.9 is going to equal norm dist. X is going to be 11.9. The mean was 12. And the standard deviation was 0.11. Cumulative, about 18%. So that's the probability. Or you could also say that that's the proportion of cans that are less than 11.9. All right? Now, P of x bar being less than 11.9 is going to equal, so equals norm.dis. X is again 11.9. The mean is still 12. The standard deviation, though, is different because this is the sample mean. So it's going to be 11.9 divided by the square root of 36, which is 6, but we take the square root of that value. The probability that a sample of 36 cans has an average amount less than 11.9 on average is negligible. It's nearly 0. Okay, so let's go ahead and report that now. So this is going to equal 0.182, and this other one is going to equal 2.45 times 10 to the negative 8th, which is equal to 0. So that's what that's going to equal. Very small. All right. So we don't need to worry about there being an average of less than 11.9 ounces in a sample of 36 cans. Okay. A study states that 12% of the U.S. population has green eyes. What is the probability that out of a random sample of 340 people, at least 32 of them have green eyes? So what's the probability that p hat is going to be greater than 32 over 340? And so what is that? 32.094. So remember that p hat, because n is much bigger than 30, this is going to be normally distributed with a mean of 1, 2, and a standard deviation of square root 0.12 times 0.88 divided by 40. And that equals 0.0176. Okay, so that's how p hat is distributed. If we want the probability that p hat is bigger than 32 over 340, that's 1 minus norm dist of 32 over 340 comma mean, which is 0.12, times standard deviation of p hat, 0.176, with 1 in the cumulative. That's going to be our answer there. If we wanted to use the binomial distribution, because this sample represents a trial of 340 people, that's going to equal the probability of x being 32 or more is going to equal 1 minus binom dot dist of 31. I'm subtracting 31 down, and the probability of success is 0.12, and the number of I think it's a number of trials first, isn't it? 340, then probability of success is 0.12, and then I want 1 because I want from 31 down. And so let's just see what we get when we put those in to Excel. All right, so let's start with the normal distribution first. So this is the probability of p hat being greater than 32 over 340. So that's going to equal 1 minus, because it's to the right, norm dot dist of 32 over 340, comma, the mean is going to be 0.12, and the standard deviation is going to be the square root of 0.12 times 0.88 divided by 340 gives us 92%. The probability that x is greater than or equal to 32 is 1 minus binom. Number of successes is 31. Number of trials is 340. And the probability of success is 0.12, so 0.9 in this case. They're in the ballpark. All right, let's go back. So this probability here was 92.9, and this one here was 94.4. These are approximately the same. The standard error of the mean is the standard deviation of the sample distribution. So remember, we had p hat is normally distributed with the population proportion p times q over n. This right here is the standard error. And then for sample means, x bar was normally distributed with a mean equal to the mean of whatever x was, and a standard deviation of the standard deviation of whatever x was divided by square root n. So this right here is the standard error, sometimes standard error of the mean, SEM or SE. And now for a quick example, if you have a population where each person or each object in that population has a mean of 23 and a standard deviation of 7, and the sample size is 25, what value is 2 standard errors below the mean? So first we need to find what the standard error is. The standard error equals sigma x over square root n equals 7 divided by square root 25, which gives us 7/5 or 1.4. What value is 2 standard errors below the mean? The mean is 23. 2 standard errors below the mean is 2 times 1.4, which equals 23 minus 2.8, equaling 20.2. Recap. What did we do today? We introduced the central limit theorem and discussed how it applied to sample means and sample proportions. We did examples and discussed standard error. Okay, and that was it. All right, everybody, have a great day, and we'll see you in class.